Hello everyone, myself B. Vishya, lecturer in chemistry, working in Indra Priyadarshini Government Degree College for Women, Nampalli. We are discussing the chapter Coordination Compounds, in which as of now we have seen the introduction of coordination compounds, in which I have started from the inorganic molecules onwards, right? So from the inorganic molecules, these molecules are of two types. One is the salts and another one is the addition or molecular compounds. Addition compounds are of again two types, double salts and complex molecules. And what are the salts we have discussed and how they will form, right? And what is the bonding takes place in the salt, and what are the additional compounds or molecular compounds also we have discussed, and in which the double salts how they formed, right? And properties of the double salts we have discussed, and complex molecules, what are the complex molecules we have discussed, and we are discussing the coordination chemistry, right? So this whole chapter is called as the coordination chemistry. The study of the coordination compounds are called as the coordination chemistry, and in which the types of the complex molecules also we have discussed. Those are of three types: cationic complexes, anionic complexes, and neutral complexes. And what are the differences between the coordination compounds and double salts also we have discussed. And today our topic is the coordination compounds. So what are the types of, what are the terms, the important terms which are used in the coordination compounds? So without the knowledge of this terminology, we cannot understand the coordination compounds. uh, if you did not watch my previous videos of the introduction part, you please watch that first. And this coordination compounds are having the certain terminology, like central metal ion, ligand, coordination sphere, coordination number, and here some oxidation state is there. In my previous video also we have discussed about this oxidation state. So this oxidation, what is the difference between the this oxidation state and this central metal ion is also carries some oxidation state? What is the difference between these two? I already told you in the my previous video. So these are the very important terminology in this particular chapter. So the first term is central metal ion. Here I have taken a cobalt complex, and in which the cobalt is the central metal ion. But in general, in a coordination complexes, in general, they represents the any metal ion is present, metal or metal ion, whatever it may be. Okay, so metal is in pure form also it can form the coordination complexes. Example is nickel tetracarbonate, in which nickel is having a zero oxidation state. So metal atom or in its ionic state also it can form a coordination compound. So in general form, the coordination compounds are represents with the means the central metal ion with the metal means M stands for the metal, and certain number of ligands are present. Certain number of ligands will be present in the coordination sphere. So this coordination sphere means the square brackets, whatever the inside the square bracket, the space inside the square brackets are called as a coordination sphere, and which may carry some charge. Okay, it may be a positive charge, or it may be a negative charge, or it may be a zero. Okay, so if it carries the positive charge, it is called as a cationic complex. If it carries a negative charge, it is called as the anionic complex. If it is a zero, it carries a zero oxidation state. So this complex is nothing but a neutral complex, and this is a general molecular formula of the coordination compounds. Okay, so here the metal is anything here, and in this particular complex we have taken the example of hexa ammonium cobalt 3, right? So the name of this particular complex hexa ammonium cobalt 3 ion. So this is the complex we have taken, and in which the cobalt is the central metal ion. That means the metal stands for the central metal ion, right? And here, what is the central metal ion? What is the central metal ion is the central metal ion which is linked with the some number of the ligands by the coordinate covalent bonds. It is surrounded by some either neutral ligands or anionic ligands. This metal ion or metal atom is surrounded by the certain number of ligands, and which all these are present in the coordination sphere only. And what is the ligand here? The ligand is, it may be a neutral compound, it may be a neutral compound, or it may be an anionic molecule, anionic compound. It may be neutral molecule like ammonia. Ammonia is here neutral molecule, and which does not having any oxidation state, as it carries a zero oxidation state, ammonia, right? So it is a neutral molecule. So ligands always should be a neutral or anionic in state, such that they must carry one lone pair of electrons. If in case of the neutral molecules, they are having a, carrying a lone pair of electrons. If it is a anionic molecule, just like all halogens, chloride, fluoride, bromide, iodide, OH minus ion, right? So all these are the anionic ligands, sulfate, SO4 minus 2, right? So all these are the anionic ligands, and they must carry at least one lone pair of electron, or the negative charge they must carry. So any one of the two they must carry, and which are capable of donate the pair of electrons. Those are called as the ligands. And here the third one important term is coordination number. So what is the coordination number here? The coordination number, normally students will think that this coordination number is nothing but the number of ligands, as I have given here. So it is somewhat correct only, but not exactly. So this means ligands here of so many types of the ligands are there, such that these are of means depends upon the donor atoms. Number of donor atoms, ligands are of different types. Monodentate ligands, bidentate, tridentate, means polydentate ligands, like that. Monodentate ligand can form only one bond with the central metal atom. So the number of ligands will be equal to the number of coordination bonds. And here for the monodentate ligand, the 6 means the number of ligands will be equal to the number of coordination bonds. For example, in this particular complex, in the same complex, cobalt complex, the structure of the cobalt complex is like this. Cobalt, which is having a octahedral geometry. So this is the structure of this particular complex. Okay, so this is the structure of this particular complex. That means, see here how many coordination bonds are there. 1, 2, 3, 4, 5, 6. 6 bonds are there, and 6 bonds around the central metal ion. Means in between the central metal ion and the ammonium ligands. So here the number of ligands are equal to the number of bonds, right? So that is the reason here it is a coordination number, means the six we can say the number of ligands and the number of coordinate covalent bonds. But actually what is the coordination number is, so this is a very important point to know actually. What is the coordination number exactly is, it is not the number of ligands, it is not the number of ligands, but it is the number of coordinate bonds coordinate bonds formed between the central metal ion and the ligands, the number of ligands. So it is the not the coordination number is nothing but, many students will think that coordination number is nothing but number of ligands, but it is not exactly. The coordination number is not the number of ligands. Instead, the coordination number is nothing but number of coordinate covalent bonds formed between the central metal ion and the ligands. The example I can give you, better I will take one new page so that we can understand easily. So here the coordination number, the same complex I am taking, the cobalt complex I am taking, and another ligand I am taking, that is ethylene diamine, and the complex is having a 3. So here the what is the coordination number of the cobalt, here is the cobalt coordination number of cobalt is 6 only. How it will be 6 is because the number of bonds formed between the ethylene diamine and the cobalt, central metal atom cobalt, is 6 bonds. Okay, so which is also carrying a 3 plus. And what is the difference between the previous compound and this compound is, this is a ethylene diamine is a bidentate ligand. That means this ligand is having a two donor atoms. And what is the molecular formula of this molecule is ethylene diamine. So CH2 and here NH, only NH only, and NH. So here this each nitrogen is carrying a lone pair of electrons so that it can donate its pair of electrons to the central metal ion. And since they are having two donor atoms are forming a two bonds at a time, coordinate covalent bonds at a time. So that here how many ligands required? 3 ligands are required. So, but what is the coordination number actually? 6 is the coordination number of the central metal ion. So, here the metal is cobalt, right? Cobalt metal. And what is the structure of this particular complex is cobalt. This is a octahedral complex only, right? Octahedral complex. And here I am just keeping nitrogens here. Okay, so this is forming a one ethylene diamine. So this is having one NH and CH2, CH2, NH. Correct? So NH, NH, CH2, CH2, this one. Okay, so NH, NH, CH2, CH2, this one. So this is the structure geometry of, means octahedral geometry of this particular complex, and this is the structure of the molecule. But how many bonds are there? Actually the coordinate covalent bonds, how many are there? How many are there? There are the 6 bonds are there. But how many How many ligands are there? The ligands are only three ligands are there. Three ligands are balancing the coordination number 6. That means three ligands can form a 6 bonds here. So this is a bidentate ligand. And see here in this particular complex, this ammonia here, the same, the donor atoms are same in both the cases. Here cobalt central metal ion is same and the ligands are different, but the donor atoms are same. So in ammonia, nitrogen is the donor atom, and in the ethylene diamine also nitrogens are the donor atoms. Okay, so this is about the coordination number. This is a very important point, coordination number, as here it is given. The 6 is the means number of ligands actually they have given, or maybe coordination number also, because it is for both purpose we can take this one coordination number. But if the ligand is bidentate or polydentate ligands, tridentate or tetradentate ligand is there, so which is having a means which can form a bonds, but how many bonds it is forming, that is the matter here. So the number of coordination bonds formed between the central metal cation and the ligands is nothing but the coordination number, but not the number of ligands. Here we need to remember this point. One more example I want to give you. If any metal is forming a coordination complex with the chelating group, the chelating agent, very famous one, that is the EDTA complex. EDTA. So EDTA is the ligand only. Ethylene diamine tetraacetate, right? Ethylene diamine tetraacetate, and any metal atom can tend to form this type of the complex with the EDTA. So even S block elements are also can form a complex with the EDTA, because EDTA is a highly stable ligand and which is a chelating agent, which acts as a chelating agent. And one EDTA can form 6 coordinate bonds at a time. 6 coordinate bonds at a time around the central metal atom or ion. So, but how many ligands? Here we are taking only one ligand. One ligand can form the 6 bonds at a time. So what is the coordination number here for the metal ion? What is the coordination number? Is this 1 or 6? 6. So the coordination number of central metal ion is 6, not 1. The 1 is the number of ligand here. So here, whatever the number we are representing here, that number represents the number of ligands as shown here and here in this particular complex. But actually what is the coordination number is, the coordination number of the central metal ion is the 6. Okay, so what is the coordination number? Number of coordinate covalent bonds formed between the central metal ion and the ligand. So this is a very important point to know. And this coordination compounds, as we have seen in this particular slide, so this is consist of two major parts, right? So this is composed of or consist of two major parts. One is the central metal ion and another one is the ligand. So here the central metal ion is any metal ion which must satisfy the three conditions. What are the three conditions? Are smaller sizes, right? Small sizes or smaller sizes. Comparatively, they must have the smaller sizes so that they can easily insert into the complex. So it is being a central metal ion, means center of the coordination. So it should have a small size in order to insert into the complex. Otherwise, it will become unstable one. The second point is they must have a variable oxidation states. So what is the variable oxidation state? What is the They must have variable oxidation states. Variable oxidation states means any metal atom, we know already the metals are nothing but the general property of the metals are the electropositivity, right? Electropositivity. What is the electropositivity? The tendency of losing the electrons. So any metal atom is having the electropositivity. That means it is having a tendency to lose an electrons. So it can lose some of the electrons, some number of electrons it can lose from its outermost orbitals and can form into a metal ions, right? Uh, Cations, metal cations it can form. So how many means cations it can form? How many number of? It depends on the number of electrons it is losing, and it can get the charge here n plus. So since it is losing the n number of electrons, and it can form a mn plus, right? Mn plus, some number of electrons it is losing. For example, I am taking the iron. So iron I am taking. Iron is having a 26, atomic number is 26 and electronic configuration is 3d6 4s2, right? 3d6 4s2. And iron can lose some two electrons from its outermost orbital, and it can form a Fe plus 2, right? By losing these two electrons from the outermost orbital, it can form a iron plus 2, right? By losing these two electrons. So what will be the configuration of iron now? 3d6. And iron can also lose the 3 electrons from its outermost orbitals. That means 2 electrons from here, 1 electron from here. It can form a, means what will be the electronic configuration? 3d5. So it can form a Fa plus 3. So by losing 2 electrons, it is forming, by losing 2 electrons, right? 2 electrons, it is forming the iron plus 2. And by losing the 3 electrons minus 3 electrons, it is forming a plus 3, right? Iron plus 3. And from here to here also, if Fe plus 2 is there in a complex or compound, so it can also, by losing 1 electron, it can form a Fe plus 3 also, right? So by losing 1 electron from here, it can form a Fa plus 3 also. So here 3d6 is the electronic configuration, here 3d5 is the electronic configuration. So, and Fa plus 3 can be reduced into Fe plus 2 also by taking one of the electron. By taking one of the electron from somewhere, it can convert into Fe plus 2 also. So because of these reasons, because of all these reasons, they must have the variable oxidation states, right? The variable oxidation states they must have. And the third one is, the third character they must carry is, in order to form a coordination complex, uh, presence of empty orbitals. The empty orbitals must present, empty d orbitals must present in the central metal ion. So since it must have a smaller sizes and variable oxidation states, and they must have a empty orbitals. So, if it is having all the three conditions, it is having three characteristics, it is having, any metal can form a coordination compound. Means any metal ion can act as a central metal ion in the coordination compounds. So Here, since all the 3D metals are the 3D series of the metal ions, or the metals are the smaller sizes, and 3D metals are having a variable oxidation states, more than one oxidation state they are carrying. Okay, more than one oxidation state. If you take a manganese as an example, manganese can form plus 2 oxidation state, plus 3, plus 4, plus 5, plus 6, and plus 7 oxidation states. So maximum number of the oxidation states they will form, right? So they are having a variable oxidation states also. And because of this property, variable oxidation states, that means they are losing the electrons from the outermost orbitals, right? Outermost orbital, so that these orbitals will become empty, right? The 3D orbitals and the orbitals of the metal ion will become empty by losing certain number of the electrons from their outermost orbitals. So here the metal ion is having a empty orbitals also. And what is the bond is taking place between this central metal ion and the ligand is, this bond is called as a coordinate bond, coordinate covalent bond. What is the bond called? Coordinate covalent bond. And this is the special type of the bond, and because of this reason there is the very strong relationship taking place between the central metal ion and the ligand. So how much strong it is the completely, when this bond takes place between the central metal ion and the ligand, they completely turning into a one new compound, one new species, so that in that the metal ion is losing completely its own properties and completely turned into one single entity. One intimacy is taking place, intimate association is taking place between the central metal atom or ion with the ligands here. So that much strong bond here it is taking place, right? So what is this coordinate covalent bond? How it is taking place here? So since here the covalent, the word covalent is there. Covalent is nothing but what? The mutual sharing of the electrons, right? Mutual sharing should be takes place. And here also the mutual sharing is taking place between the central metal ion and the ligand, but not in terms of the electrons. Here, central metal ion is having a empty d orbitals, and this metal ion is sharing its empty d orbitals, and the ligands are having a extra pair of electrons in this manner. Either they are carrying a lone pair of electrons, or they might carry a negative charge. So extra pair of electrons they are carrying, right? So in order to form a bond, the sharing should be takes place between, means the bond should be consist of the two electrons, right? But here the metal atom is having a empty orbitals and the ligands are having a pair of electrons, so that ligands are donating their pair of electrons to the empty orbitals of the central metal ion here. So in such a way that this coordinate covalent bond is forming. So because of this reason, this is a very stronger bond. And since here the metal ion is accepting the electrons from the ligand, right? This metal ion is having the empty orbitals, and which are accommodating the electrons donated by the ligands, right? So this ligands are donating the pair of electrons to the central metal cation. That is the reason they are called as the electron donors. And metal ions, since they are accepting the electrons, are called as the electron acceptors. And as per Lewis acid base theory, any element, any atom or group of atoms, whatever it may be, if they accepts the pair of electrons, they are called as Lewis acids, right? Lewis acids. So that here metal is also accepting the electrons and acting as the electron acceptor, so that this metal ion is also a Lewis acid as per Lewis acid base theory. And ligands, since they are donating the pair of electrons to the central metal cation, the orbitals of the central metal cation, they are called as the electron donors, right? Electron donors. And because of this reason, as per the Lewis acid base theory, any molecule, any atom or group of atoms or ions which donates the pair of electrons, pairs of the electrons, so those are called as a Lewis bases. So as per this theory, means this in coordination compounds, the ligands are acting as a Lewis bases here, because they are donating the pair of electrons to the central metal cation, the ligands of the central metal, sorry, the orbitals of the central metal cation. And here, I hope you understood what is the central metal ion. The central metal ion is the center of the coordination, and which is surrounded by the uh, neutral or anionic ligands, right? Neutral or anionic ligands through the coordinate covalent bonds, right? And this central metal ion is accepting the pairs of the electrons, so that they are called as the electron acceptors. And because of this, the metals are acting as a Lewis acids as per the Lewis acid base theory. And ligands are the electron donors, which are having a ability to donate the pair of electrons. So these ligands are called as the electron donors. And because of this electron donating property of the ligands, these ligands are considered as the Lewis bases as per Lewis acid base theory. Coordination compounds are containing the two important parts, right? Each coordination compound is containing the two parts. What are the two parts? Just now we have seen till now, there are the central metal cation, right? Central metal cation and ligand, and some number of the ligand. These ligands are number. It may be one, it may be two, it may be three, it may be, actually it is more than two only, right? More than at least one. So silver complexes and mercury complexes can form with the two ligands also, linear molecules. Those are the linear molecules, and this is more than two. Okay. Uh, so n is greater than or equal to 2. So here this coordination compounds are composed of the main two parts. One is the central metal cation. This is the central metal cation, and the second one is the some number of ligands. Ligands. So what are the central metal cation and what are the ligands? Let us see now. And central metal cation, here we represents normally the metal ion, central metal cation with the M, right? M. And this M is carrying, means it is accepting some of the electrons donated by the ligands here. So this central metal cation which is accepting some of the electrons, from the ligands. And here the central metal cation is acting as an electron acceptor. Why? Because it is accepting the electrons from the central metal cation, and this is the center of the coordination sphere. So how the structure will be? The metal atom is at the center, and which is surrounded by the some number of ligands here. So coordination number 6 I'm taking. So if the coordination number 6, the 6 ligands are surrounded by the central metal cation. right? Central metal cation. And how the central metal cation is accepting the electrons. See here, metal ion, the metals are having one of the important property that is called as a electropositive nature, right? Metals are having a the inbuilt character, that is so, which is having electropositive nature. Electropositivity is nothing but what? The tendency to lose an electrons. So to form a coordination compound, to form a coordination complex, any metal need to have some three conditions. What are the three conditions? Are, it must have a smaller size, small sizes they must have, the first thing. Okay, they must have a variable oxidation states. Variable oxidation states, variable oxidation states are nothing but what? The means more than one oxidation state they must have. For example, iron is there, iron is there, it can form two types of the oxidation states. So iron plus 2 it can form, means these are the stable oxidation states for the iron. Iron plus 3 also it can form. How this iron is forming a plus 2 and plus 3 oxidation state? This iron is converting into Fe plus 2 by losing 2 electrons, right? By losing 2 electrons it is forming into iron plus 2. And iron also it is losing plus 3 electrons and forming into a plus 3 oxidation state. And there is a transaction of the electrons will be takes place between this iron plus 2 and iron plus 3 also. That means iron plus 2 can be converted into iron plus 3, and similar way instantaneously, simultaneously, iron plus 3 is also can convert into the iron plus 2 also. So this kind of mechanism should be there in the central metal cation. So variable oxidation states means more than one oxidation state they have to form. So these are called as the variable oxidation states. And the presence of d orbitals, the presence of d orbitals must be there. So presence of d orbitals. So since if they are having a variable oxidation state is nothing but what? Positive oxidation state means. So how it will form? Sorry, it is by losing 3 electrons. So losing indicates that negative symbol, right? Minus symbol. So, they are losing the electrons from their outermost orbitals. Obviously, their outermost orbitals will become empty. So, presence of empty d orbitals. This is also very important point. So, since the metal cation, the central metal cation is having a empty d orbitals, means any metal ion which must obey by, which must have these three conditions, that is smaller size, variable oxidation states, and presence of empty d orbitals. If any central metal cation, means any metal is having these three conditions, three are there, so it can form a complex, coordination complex. So since this metal ion is having a empty d orbitals, this is having a empty d orbitals, and the ligands are having a extra pair of electrons or negative charges they must carry. So these ligands are donating their extra electrons to the empty orbitals of the central metal ion. And here the metal is accepting the electrons. Here the ligands are donating the electrons to the central metal cation. And since it is accepting the pair of electrons from the ligand, from each ligand it is accepting the pair of electrons. See here, central metal cation is surrounded by the 6 ligands, and 6 ligands are donating the pair of electrons to the this metal ion here. So how many total number of electrons it is accepting actually? 2 plus 2, 4 plus 2, 6, 6 plus 2, 8, 8 plus 2, 10, 10 plus 2, 12. Totally 12 electrons it is accepting from the 6 ligands, right? So to the empty d orbitals. So that is the reason this metal ion is called as the electron acceptor, and in ligands are called as the electron donors here because they are donating the pair of electrons. In this way, the combination of these two, because metal ions are having a empty d orbitals, and to the empty d orbitals, the ligands are donating their pair of the electrons to the empty d orbitals of the metal. In this way, the coordination covalent bond will be formed between the this central metal cation and the ligands. So this kind of the molecules are called as the coordination compounds, and here the metal ion is also called as the Lewis acid. Why it is called as the Lewis acid? Since it is accepting a electron pair from the ligands. So according to Lewis acid base theory, any molecule, any atom or group of atom or ion which accepts the pair of electrons called as the Lewis acids. And similar way, as per the same theory, that is Lewis acid base theory, anything, any atom or group of atoms or ions or molecules, molecular ions, anything which donate the pair of electrons to the central metal cation or any other element which donates, means electron donors, are called as a Lewis bases. So there is a very stable bond is taking place between this central metal cation and the ligands here. That is the reason they are very stable. So this which results the coordination covalent bond, and this results the coordination compounds or complexes, right?